Hello, my name is Don Metzger. This video shows how to use equalization to improve the EVM measured for a communication signal using an Analog Devices AD9082 MxFE chip. We'll show you a little bit about equalization and describe that, then we'll move on to show the measurement setup, then we'll do a demo, dive right in, and we'll show without equalization, and then with adaptive equalization, with fixed equalization, and then with fixed and adaptive equalization, and then we'll summarize. Equalization is a technique for compensating for the imperfections which occur between the transmission of a signal and the reception of a signal. Those imperfections could occur due to problems in the transmitter, or things in the channel, how the signal propagates from the transmitter to the receiver, or things in the receiver itself. Equalization is typically implemented using an FIR filter with complex valued tap coefficients. Now, why complex valued tap coefficients? Well, if an FIR filter has real valued tap coefficients, then the frequency response below the center frequency and above the center frequency are the same. They're just mirror images of each other. However, if the FIR filter has complex valued tap coefficients, then that constraint no longer applies, and there can be a different response in the negative frequency space and in the positive frequency space, like in the plot to the right. The response of this FIR filter with complex taps is different to the left of the center than it is to the right. And that's what we want when we do equalization. So it's no more sophisticated than just an FIR filter, except that the tap coefficients are complex valued rather than the typical real valued coefficients. Fixed equalization keeps those tap coefficients constant. They're the same all the time. Adaptive equalization is constantly changing the tap coefficients and updating them. Here's the measurement setup we'll be using. We have a Xilinx ZCU102 host board that is running Analog Devices IIO software. That's the green board in the picture. And then the little blue board is an Analog Devices AD9082 FMCA EBZ evaluation board. On the DAC side, the 9082 has 16-bit 12 gigasample per second DACs. The input-output rate is 1.5 gigasamples per second. On the ADC side, it's 12-bit 6 gigasample per second with an input-output rate also at 1.5 gigasamples per second. The DAC 0 output is looped back to the ADC 0 input using SMA cable. For a signal, we're going to use an 8 PSK waveform at 500 megasymbols per second, which gives us about a 500 megahertz usable bandwidth. We'll center that at an 800 megahertz center frequency. For software, we'll be using a quick transceiver by Quick Systems. If we zoom in and look at the eval board closer, you can see the chip underneath that heat sink in the top right of the picture there. First thing that happens to the signals in or out of the chip is they go through balance. That's because inside the chip it's all done differential RF, but typically out on a PC board we're doing unbalanced connections, and so we have baluns that convert from unbalanced to balanced and back. Also, we have transmission lines, we have launches that convert from the transmission lines to the SMA cables that we're using. All of these components are imperfect. And the trick in doing good RF design is to use these cost-effective, imperfect, different components and get better performance than we would expect from the raw performance of these particular components. After starting up Quick Transceiver, first of all we want to let the software know what system we're working with. We're going to be working with an AD9082 that's hooked up to a ZCU 102 board. We'll be talking to it over the network, and there's its IP address. We also want to talk to the 9082 and control it. So we'll be using DAC 0 at 800 megahertz and ADC 0 at 800 megahertz. We'll be getting 660,000 samples of acquired data, and then we'll be using the 1.5 gigasample per second data rate external to the chip. We also want to make sure we've got the right windows up. I'll be using acquired waveform, acquired spectrum, acquired persistent spectrum, the constellation, a couple of adaptive EQ plots, and then some measured results. Finally, we want to call up our transmitter file, which is that 8PSK waveform at 500 megasymbols per second, root raised cosine alpha of 0.3. And then we just go hit the start button and we begin transmitting and receiving and demodulating the 8PSK waveform. So up here in the measured results, we can see it's an 8PSK, the symbol rate's 500 megasymbols per second, carrier frequency is 800 megahertz, and the occupied bandwidth is a little over 500 megahertz. So this is a pretty big, broad signal that is coming through. I think I'll stop the measurements for a second and take a look at some things in the measured results here. The carrier to noise ratio is measured on the spectrum here. This is carrier, this is noise. So carrier to noise is a ratio between these levels here. And this value is 51.4 dB. This begins to set our expectation. This is just due to the spectrum of the signal and shows us how much carrier power we have compared with the noise floor of the receiver. We're hoping as we go through a whole demod process that we end up with a final set of symbols that has a similar signal to noise ratio. So that signal to noise ratio, when we're done with the demod, is known as EVM. So we can look here at the EVM line and see that it's about 3.93% minus 28 dB. This minus 28 dB does not compare very well to the 50 dB that we're expecting from a signal to noise ratio standpoint. We've lost more than 20 dB of dynamic range in the system as we've gone through this demod. And it's not due to thermal noise. The thermal noise floor is right here. This is actually being caused by this EVM is being caused not by noise, but in this case by other components in the system. Now let's turn on some adaptive equalization. I'm going to start the system running again, and then I'm going to go to Processing PSK QAM, and I'm just going to click the adaptive equalization. We'll be using 33 complex taps in this analysis. And as soon as I apply that, you'll notice what happens to the final constellation. Those points got much, much smaller in there. And over here, these two plots are now showing us the adaptive equalization coefficients, and we can display those as magnitude, phase, real, imaginary, whatever we want to see about the coefficients. You can see they're largely real. There's a big real component right here in the middle and a little bit of smaller coefficients off to the side. Here's actually the frequency response of these tap coefficients. And you can see in this case, again, this non-symmetric below the center frequency and above the center frequency, they're not the same, and that's what we get when we use complex valued FIR filters. I'm going to stop this for just a second. Let's go in and look. There's our carrier to noise ratio, 51.6. It was 51.4 before, very similar result to what we were seeing. But now look at the EVM, 0.28%. That was almost 4% before. And in terms of dB, this is minus 51.2 dB. So in this particular capture, the carrier to noise was 51.6 and the EVM is 51.2, minus 51.2. So we're almost getting theoretically the same signal to noise ratio on the final symbols as we had on the carrier to noise ratio on the input spectrum. So our adaptive equalization has improved the EVM of our measured waveform significantly, more than 20 dB improvement on this. Let me show you how to convert from adaptive equalization to fixed equalization. Let's go up here and right-click on the adaptive EQ coefficients and click on Save Coefficients to File. So that'll bring up a dialog, and let's just save these as complex FIR coefficients in this little text file format that we have for saving those. Now I'm going to go over here and I'm going back to the PSK QAM and I'm going to turn off the adaptive equalization. So do not do adaptive equalization. But I'm going to go up here to the receiver waveform processing and tell it to turn on the complex FIR filter and use those coefficients that we just stored. Receiver processing is all done in software. These are different things that we can do to the data after we get it from the 9082. We could shift it in frequency or interpolate or decimate it. We've got some filters that could be applied, and this is the fixed equalization that can also be applied using the stored coefficients in a file. All right, now let's go up and start up the system again. Now in this case, we're not going to see adaptive equalization coefficients because adaptive equalization has been turned off. We're just using a fixed set of coefficients that's been stored in a file. So the equalization is the same every time. It's just whatever those complex tap coefficients were in that file when we saved them. But you can see that the EVM is still very good. Maybe not quite as good as the adaptive equalization, but still very good in quality. Finally, we can go up here and we could actually turn the adaptive equalization on as well. So now we'll be using the fixed equalization, and then the adaptive equalization will clean up whatever's left in the whole thing. And you can see the adaptive equalization is actually, I'm going to stop it so the plot's not hopping around. You can see it's 0.006 of a dB. The adaptive equalization is basically saying, you know what, there's not much to clean up here. The fixed equalization is doing almost everything, and so the adaptive equalization has almost nothing to do here. And again, our EVMs are very good. But you might be saying, isn't this cheating a little bit? I mean, we used an 8 PSK waveform to generate the tap coefficients, and then we're running the 8 PSK waveform through it. Maybe that's cheating a little bit. So I hear that. Let's go and make a change to the system, use a totally different waveform. First of all, I'm going to go in here and I'm going to turn off adaptive equalization. I'm going to leave, first of all, I'm going to turn off the fixed equalization. Now let's go call up a different waveform altogether than our 8 PSK waveform. So I've pre-made a couple of those. Let's do a DVB S2X type of waveform. This is a 64 APSK waveform. It's got framing, it's got a different symbol rate of 400 megasymbols a second, totally different modulation type, and so forth. So altogether a different waveform. I'm going to have to acquire a little bit more data for this, so I'm going to go up to 100,000 acquired samples to make sure I get a full frame's worth of data here. Alright, so this is it. There is no equalization being applied at the moment, and you can see here's our signal to noise ratio right around that 50 dB carrier to noise ratio point, and our EVM is 4% minus 28 or so dB. You can see the spread on all of the final constellation points. Now let's go in and turn on that fixed equalization. So these are the tap coefficients that were generated when we did the 8 PSK waveform at a different symbol rate and different usable bandwidth and everything like that. And as soon as we turn on that, then we're back again to the good EVM case. You can see the final symbol constellation points here, and I'll stop it. And so carrier to noise is about 49.3 dB. The final EVM is minus 49.1. So again, we're very close to the theoretical signal to noise ratio that we would expect. But you may be saying, well, I don't like round constellations. I kind of like square constellations. So let's try something else. So let's go up, and again, let's turn off the fixed equalization. Let's go grab a different waveform. In this case, let's pull up a 256 QAM at 375 megasymbols a second. Totally different symbol rate, modulation type. So there's that. We'll start it up again, and you can see the constellation points here. I mean, this is almost to the point that there's almost no margin in this. If we add much noise to this system, we're not going to get a good, we're going to start having lots of symbol errors and things like that. And this is just loopback cable. There's no channel in there or anything. So we're just on the borderline of starting to cause significant symbol errors just due to the imperfections in the RF system. So let's go in and turn on our complex FIR filter, doing our fixed equalization, and as soon as we do it, boom, we've got that nice 256 QAM constellation, and again the EVM is approaching something on the order of 50 dB. So let's summarize what we have seen. There's a table that summarizes what we saw for the 8 PSK waveform. If we did not have either fixed equalization or adaptive equalization turned on, no equalization at all, we saw an EVM around 3.9% or minus 28 dB down. Probably kind of disappointing, where we were hoping for better than that. If we didn't do fixed, but we turned on the adaptive equalization, immediate improvement, the EVM went down to about 0.3 and minus 51 dB down. Then we saved the tap coefficients and we just used fixed equalization using those with no adaptive equalization turned on. And again, the numbers were about 0.3% or minus 51 dB. And then if we turned on both the fixed and the adaptive, really no improvement there over the fixed case. There wasn't much left to clean up for the adaptive equalization. So a very impressive 23 dB improvement in EVM by using equalization. Let's just step back for a second and think about this from a broader perspective. We have a mathematical algorithm, which is this complex FIR filter, and we are training that algorithm with some data. In this case, we ran that 8 PSK waveform through it. And then we use that trained state, those tap coefficients for the complex FIR filter, we use that trained state to perform some useful task, which in this case was improving the EVM of our waveform. Nowadays we call that type of a process AI. It turns out that in communications we've been doing AI for decades, just not calling it AI. We were doing AI before it was cool. If you want to tell your boss that you're using AI in your job, I think that's perfectly acceptable. Alright, that's it for this video. For more information about Quick Transceiver, you can visit us on our website at quicksystems.com, or you can send us an email at sales@quicksystems.com. Have a good day.